Hi there, I'm Joey, and this is my latest project. So essentially, it's a Geiger counter with built-in Wi-Fi. Now a Geiger counter is a device that measures ionizing radiation by use of this neat little gadget here called a Geiger molar tube. So this tube, it's a glass tube with a conductive coating applied to the inside, and running down the middle you can see here is an electrode. And that electrode is supplied with about 400 volts of DC power, but it's electrically insulated from the outside glass. So no current flows or anything. However, when a particle of ionizing radiation comes in, so for example a gamma ray or a beta particle, it's going to fly in, and because it's ionizing radiation, it's going to ionize some of the gas inside the tube, and therefore, once it's ionized, that high voltage potential is going to accelerate those particles, and those particles are going to land on the filamentary tube, and so that means that they're going to supply their charge into there, and that means that essentially a tiny amount of current will flow each time that a ionizing particle comes in. So if you can detect that tiny little bump of current, you can basically treat that as a radiation event and count those. And if you count those up, you basically figure out how many particles of radiation are coming in and striking this tube. Now you don't get any idea of the energy of each radiation particle, you just get one event no matter how much energy is actually carried. So it's not giving you an idea of radioactive dose, since you care more about how much energy per particle comes in for that, but it does give you a general idea of the amount of radiation around. So just a quick tour of how it's built. There's a mini USB port here, so this thing actually gets powered by just plugging in USB cable like this, and then on the other end, you just plug it into this USB battery bank that I've got here. And now it's powered up. I'm not sure if the microphone picks up, but there's an extremely high-pitched sound that comes out of it. I assume it's coil whine, but it's probably like 18 kilohertz or something like that. But anyway, that powers it up. So then I'm going to unplug it here just so I don't get zapped. So that powers up over here. There's a high voltage boost circuit, which is why there's this huge inductor on here, and that actually supplies the 400 volts to the tube through this end, and then the other end is where you get your output. So then the output goes through some conditioning components. I've got an op amp here, actually configured as a buffer, because again, you can't take any current off this. Even if you just put in a GPIO pin, you're not going to be able to measure anything because the GPIO pin has too high of input impedance, or too low of input impedance. It draws power from this, even though we idealize it as not doing so. But then that goes into a GPIO pin on this ESP8266, which you can see here has built-in Wi-Fi through that antenna. I also add in a programming header here just in case, but that's soldered to the board, and then that actually serves as a Wi-Fi access point that you can connect to and view what it's picking up. So now for a little demo of it working. I've had it running for a couple minutes to get a baseline, and now I've got this pellet of americium that I'm going to put on the detector, which should give it more radiation, and we should see an uptick. So I connect to my network, the ESP web server, and I'll type in radiation. And now that we're connected to the Wi-Fi network, we can go up here to 192.168.4.1, and we see that we've got just about 600 counts in the past 60 seconds, so that's way higher than the 20 we were having before. It's gotten 3,600 total counts, and we've been up for 13 minutes, so that's a really good check to know that it hasn't had any reset since I turned it on in the past 13 minutes. So on average, we've had 262 counts per minute. Now if I go up here and I go to /CSV, and I can open it with LibreOffice Calc, which is just a spreadsheet program, then we can load that in, and it shows all of the minutes that this has been on since the time that I actually created it. And if we go down to the bottom here, we'll see the numbers reset and then we can look at the most recent startup. So we see for the first 6 minutes or so, we had perfectly normal, roughly in the range of 20, with a little bit of randomness, of course, and then the moment I put the Americium on, it went way up. So that's really confirming that the whole system works, that we're logging, and all kinds of other interesting information. So I designed this board myself in KiCad or KiCad, KiCad. I hear people say all kinds of different pronunciations, so I'm just going to say potassium iodide CAD. I sent the board files off to Oshpark, and then I soldered it together just with my little stand here. This is all I have in terms of soldering equipment. I don't have any fancy little holders or microscope or anything like that. I actually just bought this off a friend right as the pandemic started. Normally I use the equipment that's available at my school, but now of course everything's shut down for COVID, so I'm stuck in my apartment and got to make do with what I have. But anyway, so the design of this board is derived from an earlier project I made, which is derived from a very, very bare bones Geiger counter. Right here. So this board is one that I bought direct from China several months ago, and it's super simple. You can see it's all through-hole components. It's got a built-in little clicky device that gives the standard click you expect from Geiger counters. And it has just a 5-volt ground and output port. So I have that going into this little board here, and then through USB cable, and same deal, it just plugs into the battery bank. So you can see here with it powered on. Of course I don't have the Geiger tube installed, so it's not going to do anything, but that gives an idea. So the signal goes down here, and then this processes it. I had to make some small modifications to the board. You can see I have a bodge wire soldered on here, and I had to cut one or two other traces. I just had to reconfigure a few of the properties of the conditioning circuit, but this is basically the prototype, and I turned it into this board, which works pretty well, I'd say. Little reset button here for the microcontroller just in case. There's also solder pad jumper here. I don't know how to get this to focus. I just bought this camera for 20 bucks off Craigslist just to make this video. But anyway, there's a solder pad jumper here to actually put it into programming mode. So yeah, let's hop over to the computer just to look at the design files for a little bit. Alright, so now we're in potassium iodide CAD, and we're looking at the schematic. So I put a fair bit of time into trying to make the schematic look as pretty as I could. So I divided things into sections and everything, made sure there aren't any like crisscrossing wires, everything's as clear as possible. So let's start up here. So we've got some power supply filtering. So from the USB connector, you can see we're not using the data lines, we're just taking in the 5 volts, capacitor and inductor to stabilize it, and that produces the 5 volts bus, and then we have a 3.3 volt just linear regulator, cheap little thing, providing the 3.3 volts that the ESP8266 relies on. So once that 5 volts is generated, then we move over to here. So we've got a 555 timer set up in astable mode with these 2 resistors and capacitors. So it's just charging and discharging this capacitor, and that is toggling this output, which generates what we can see here, the 555 square wave signal. Of course the 555 also has these decoupling capacitors. Probably doesn't super need them because it's just a 555, but putting them in there as good practice. So once that square wave is generated, we come down, I think, over to here. Yep, so that goes in, and that is toggling this transistor. So this is just a NPN transistor, but it's rated for higher voltage than usual. And that's because that is taking the square wave and it's turning this inductor on and off. So this is a 10 millihenry inductor, which is fairly large. That's the big chunky box I pointed out on the board. So when we start current flowing through this inductor, we then stop the current, we stop the voltage across the inductor, but the inductor keeps the current going, which produces a high voltage spike, which is why we need a higher voltage tolerant transistor. And those big high voltage spikes go off as the inductor spikes signal that you can see here. There's also on this output here basically is a normal NPN transistor, just a 3904, the cheapest little one you find anytime, with a pull-up resistor, and that produces the 555 feedback signal, which, if we look back up here, is attached to the reset pin, which I think should be called the enable pin for a 555, but the point is that if that's pulled low, then the 555 will not be operating and will not produce the square wave. So essentially, if the voltage is high enough to turn on this transistor, the 555 will stop producing its square wave and will stop getting these inductor spikes. So once the inductor spikes are produced, they go up here into what's called a Cockcroft-Walton voltage multiplier. Basically, you can think of it as this arrangement of diodes and capacitors allows you to charge the capacitors in parallel, and then through the diodes, they basically get stacked on top of each other, so they're charged in parallel and then discharged in series. So if you have spikes of 100 volts each, then you can stack multiple ones on top of each other to get higher voltage. So here we have these three capacitors which allow us to do that. And then through a 10 megohm resistor, because although this is nice for getting high voltages, it's a very low current supply, so we want to make sure that we're not trying to draw more current than this can supply. So there's the 10 megohm resistor, which goes to HV supply. So basically through these three circuits here, the 555, which makes the which makes the square wave, into this that turns that square wave into inductor spikes with feedback to shut down when needed. And then once we have those inductor spikes, we stack them on top of each other with the Cockcroft-Walton voltage multiplier, and that's how we get our high voltage supply. Now that high voltage supply goes into the Geiger tube, and you can kind of see from the symbol here that there's no way for current to flow through, but as we discussed earlier, when a particle comes in, current does essentially flow. It's not the normal way we think of current as we're putting electrons in and those electrons are coming out the other side. It's the fact that those ionized particles are hitting and depositing their charge, and that's what's coming out of here. So from there, we've got those particles that go into this capacitor, and that holds the signal high for a little bit, which allows it to turn on this transistor. Once that's turned on, it pulls this low rather than the pull-up that's here, and that goes into this op-amp, which is configured as a buffer, because again, this really can't supply hardly any current. When I tried not having this buffer, I just totally saw the signal get killed off by having it connected to the input to the microcontroller. But anyway, once the buffer has done its job of buffering that signal, it becomes the Geiger pulse that you can rely on. Now that Geiger pulse actually goes to two different places. So one place it goes here is this monostable 555. So monostable basically means when it gets a signal, it will give an output of a known duration. These signals that come in are on the order of milliseconds, and we want to be able to flash an LED for user feedback. Now on the board I have, this actually isn't working, so you may have seen the red LED on the back was solid on. I need to look into that, but I don't have an oscilloscope, so I can't really test it that well. Anyway, though, the Geiger pulses come into the trigger pin, and then it uses this resistor and capacitor to create a pulse of known duration, which then goes through the out pin, current limiting resistor, of course, for our LED, which gets powered by the 555 directly. Now we have the Geiger pulse that gives the direct visual feedback through the LED with this 555, but we also have Geiger pulse going into the microcontroller here. So the microcontroller is set up in a pretty minimal configuration. I just have the exact resistors we need to allow it to run. Reset pin here is pulled up by this resistor, but the push button that we mentioned before goes to ground. Enable pin is pulled high, so it's always enabled. Decoupling capacitors here, connected to RX and TX lines for reprogramming if needed. GPIO 0 is how you toggle reprogramming, so pull it high for running, and I have the solder jumper here so that if I need to reprogram this, which I don't expect to need to, I can pull it to ground and be good to go. Then here we have 15 also pulled to ground. Programming header is listed here. We just have the RX, TX, and ground. Then a test point for high voltage through another big resistor, just because you seriously can draw any current off that high voltage. Even just putting your multimeter on is going to make the voltage be much lower than you expect. So yeah, that's a basic idea of the circuit. Power supply filtering. These three generate high voltage for the tube, and then through the tube we get signals which get buffered and then get sent to our outputs, which are the Wi-Fi and the LED flasher. Now if we want to pull up the board file for this, okay, so here's the board file. So you can see this green is a ground pour on the back, and we've got our inductor over here. 5 volts comes in. We've got these three big capacitors for our main voltage rails. So we've got the 5 volts raw from the USB, and then we've got our 5 volts, which has gone through a small inductor for stabilizing the current, and then another one for our 3 volt bus coming off of the voltage regulator here. Over here we have the Cockcroft-Walton, which has the 3 LEDs, or 3 diodes, not LEDs, and the capacitors that go together to stack up and make our high voltage. There's not a whole lot to this board really. We can go and view the 3D model. This is actually the second version that I hope to produce, which is very similar to the one that you just saw. But the big changes are that I changed the USB port so that instead of needing to have a big cable that runs to power it up, it actually has an onboard USB. So this actually has the board shoved directly into the USB port of the power supply. So that's nice because it compactifies the whole thing, and also I don't have to pay for the part of installing a USB connector. College budgets make you do fun things. Okay, so here's the software that's running on the board. So it creates a ESP web server, so you can just connect to that with your phone or anything else. I actually didn't mention why I wanted Wi-Fi. The big reason is that I had the original Geiger counter that just had the simple through-hole board, and I liked that, it made little clicking sounds, but I wanted to be able to actually see, numerical outputs of how many counts per minute it was measuring. But I also figured out that putting a screen on a device that I make is kind of difficult. And most of the screens I can get are like really small and not high quality. They'd also be fragile. I want to be able to keep this device just in my backpack so that whenever I'm curious if I might have something radioactive, that I can just pop it out and find out. So I thought about it and I realized that I have a screen that I carry around in my pocket every day. It's my phone. So if I could just connect my phone to the ESP that's on the board, then my phone could show everything that I need for the Wi-Fi outputs. So yeah, that works really well. So I just connect, I put in the password, which I just have set to radiation. It doesn't really need to be secure. I don't expect anyone to be connecting this besides me. So it goes into input pin 5, and then I actually have basically a system of bins, I call it. So it allows the system to keep track of the past minute of incoming radiation and also tell you if the radiation is changing. Essentially, this is the best way I could think of to code in to be able to constantly update how many counts have come in the past minute. So every 5 seconds, it adds up how many incoming radiation events have happened in the past 5 seconds and adds them, and also will go back to a minute ago and wipe out that 5-second block. So it works pretty well. Basically, it's just constantly going through into the next bin every 5 seconds to load the data into. We just start up a server and we will show the counts in the past. In this case, we have set to 60 seconds, and then it'll show the total count since startup, and how many minutes it's been running since startup, which is really good because it allows you to detect resets. If you've had it running for 10 minutes and it says 3 minutes since startup, there was a reset 3 minutes ago. It also tells you average counts per minute since startup, so it allows you to get an idea of the baseline. So that's really useful if you want to just set this up in a spot. If it's a place you think might have slightly more radiation, then you can set it up there and run it for an hour, 2 hours, whatever you want, and it'll take up what the average counts per minute is. All of the data for how much has come in for every minute is also stored in a CSV file that you can download. So yeah, it stores that to the SPIFs file system in a CSV, which works really well. Basically allows you to store things to the onboard flash, which is great. Let's see. Yeah, and it attaches an interrupt to the signal pin from the Geiger counter, and that's how we actually detect the counts coming in. So every time an interrupt happens, it adds up this queued counts, and then in our void loop, we're figuring out how many queued counts have happened, and for each one, we decrement the queued counts then. We add 1 to full counts, and then add 1 to whatever the current bin we're in is. And then every time that we are going up in our runtime that we've been active for with the milliseconds function. So if it has gone up to the next second, so it updates every second basically, then it'll switch bins if it needs to. And one final thing I wanted to talk about is the resources I used for this project. So all of the parts were ordered from DigiKey, which is a really solid site that you can buy electronics from. The best thing about DigiKey, I think, is their search features. So for example, in this project I was being powered by 5 volts USB, and I needed 3.3 volts to power up the microcontroller. So all I did was I went here and I searched voltage regulator, and then here we go. I wanted a linear regulator because they're simple and cheap. Then over here it looks like we have voltage output, and we know that we want a fixed 3.3 volt output. So we go here, and let's say we'll get 10 of them. I want to have enough to be able to solder it on, and if I accidentally ruin one, I'll still be okay. And once we apply that, I sort by lowest price, and there we go. This one is 11 cents each, and that's actually the one I went with. So yeah, really great search features. Also, DigiKey has this tutorial series, which is what I used. This is actually the first project I've done that used potassium iodide CAD. In the past I've used Eagle, but one of the big goals I had for this project actually was to use only open source software to make it. So I used Linux as my operating system. It was programmed with Arduino. The circuit board and schematic was designed with this software instead of Eagle, and heck, the video is being edited with Shotcut. So really nice to be able to only use open source software and make a whole project like this. The boards I ordered from Oshpark. They make it really easy to upload your zip file of your project. You don't even need to export Gerbers, which is an annoying little process that can sometimes have issues. So I was very happy with Oshpark. They sent me 3 boards, quick shipping, and I'll certainly use them in the future. So for future, as you can see from earlier, I've got this second version I'd like to make with the built-in USB connector. I've also seen a little bit of issues with the voltage booster, which I'd like to work out, but unfortunately without an oscilloscope that's hard to do. I'll also be sharing the files for this project on GitHub, including both the board design and the software that actually runs on the microcontroller. Once I get the electronic design settled, I'd like to 3D print up a nice little case for it and be able to carry around a convenient small Geiger counter. I hope you were interested in this project, and I will look into doing more in the future. Thanks for watching this pretty long video.